So the materials has been categorized into, like, for example, two categories. Okay, conductor, or three categories. Conductor. So what's a conductor? It's a signature beer in Steamworks. 9.2% alcohol. It's IPA. And no kind of, there's no discount during happy hours because it's high alcohol.
Oh, really?
Yeah. Everything else will be like $2, $3. It's still $9. Shit.
Yeah, it's not our favorite anymore. What was the cheaper one?
Like copper, right? These are conductors, insulator, rubber or glass. Yeah, aren't they? Silicon dioxide. Or semiconductor. So the conductivity is between these two types of materials, right? You know, if you look at the periodic table, and I couldn't remember that. So there's a, so that's group. So these are the groups, right? If you look at it, you'll see groups. So analog will cover this intensively later. So I have to learn it anyway. And these are important, especially, you know, there might be some interview questions that are going to ask. Quite a few of them will be asked if you are interviewing with a company like that. Group of 3, 4, 5, 6 on the table. Okay, I'm not doing everything, but just these specific groups, and labeled as 6, 7, 8. Carbon, is that nitride? And oxygen. 14, that's silicon. 15, phosphorus. And 31 is gallium. 32, germanium. Pronounce it, remember. 33 is arsenide. So these are semiconductor materials, are usually 4 and 5. These. So each group has the same. Each group has the same number of electrons in the outer orbit. So for these, right? So these, so carbon, silicon, germanium has the same number of outer orbit electrons. Have you learned it somewhere else?
Yeah.
Okay. Physics 2? Chem 1? So for example, silicon, how many protons in silicon atom? How many protons? Yeah, 14, I labeled that for you, right? So 14. So for silicon, it has plus 14. That's a proton. So how many electrons here for this layer? Yeah. Right? So if 1 here, then it's going to be 2. 8. And how many left? 4. So there are 4 outer orbit. I think so, yeah.
Some of them, like chlorine, can get more than 8 in its family shell.
You see, it's not 1, not 2, so that's why it's not a conductor, right? If there's only 1, which means not too many of them are there, it can freely move to other places. It's usually a conductor. But 4 is not 1, not 2, so it's not conductor, right? So it's a semiconductor. And so what are the names of these electrons? Yeah? Involved in what? Yeah, what are they called? Involved in chemical bonds, right? That's a term of it. So for silicon and you know, the semiconductor materials, they do not just use silicon. Right? They grab a piece of silicon wafer and they dope it with a dopant. Can be phosphorus, can be boron. And the phosphorus has how many valence of electrons? 5. So it's 15 protons, right? So it's 2. Okay. So at the very beginning, for the it's called intrinsic silicon, which is not doped silicon. Have you learned that analog yet? Not yet. Probably a couple weeks. Yeah, a couple weeks later, you'll get into it. P-n junctions, right? Delts. Very soon, intrinsic silicon. It's not doped. And how to dope intrinsic silicon with phosphorus? High pressure, high temperature. I think Dr. Jessing is the expert on that. He will probably introduce like how to make a how to say that? It's not intrinsic anymore, so it's a doped silicon wafer. So if you dope P in there, it's very interesting. Just don't get confused. So there are mainly two types of semiconductors: P type and N type. And if you dope phosphorus into the silicon, so at the very beginning, how many valence electrons for silicon? 4, right? Because the material has all these crystals, so the atoms are getting together to each other. This is, for example, this is a valence electron from this silicon atom. It has 4, right? Ignore this one for now. It has 4, right? And get another one over here. It's going to contribute 1 electron to form a what? What is that called? Yeah, covalent bond. ANT. No. For what? Required for what? Oh, for the yeah, we just updated last year. If that thing is important, it was not in there. But you don't have to. You don't have to. No, it's very simple. I just introduced. I'm not expert on that as well, so no worries, no pressure. You just need to know what I'm writing on this paper. Yeah, make sense? So you know what are protons, atoms in physics 2? Do they teach this kind of thing in physics 2?
I mean, they just go over the atom very,
okay.
very brief.
Yeah. Okay. All right. That's a piece of silicon. I don't know how many atoms are in there. Many, right? So they are forming these covalent bonds because they are next to each other. And definitely you got one here as well, because it has 4 valence electrons. So it's going to form a bond here as well. Make sense? So you got another one here, and it's going to contribute an electron to make a bond. It's going to contribute an electron to make a bond. I should label this one red as well. That's how that works. I just didn't draw all of the other ones. There are just so many, right? Okay, if you dope phosphorus into this intrinsic silicon wafer, what's going to happen? So it is able to replace some of the silicon atoms in there. However, this guy has 5. Are these electrons also involved in covalent bonds? No, only these ones, right? So we're ignoring all the other ones. Just look at the 5, this number here. So how many electrons this guy has? Valence electrons, 5. Okay. So what if this guy? What if a silicon atom is being replaced by a phosphorus atom in that silicon wafer? They just put that silicon wafer into that, I forgot the name of it, like oven or something, at a pressure, and so there might be a spray or something spraying that phosphorus atoms in there, high temperature, high pressure. When it reaches a specific condition, it is able to dope that material into the silicon wafer to replace the silicon atoms in the crystal, and it becomes remember, each one is contributing 1 here to the middle one. So you have a P here right now. P has 5, right? So it has 1 to form 1 covalent bond. Another one, 1, 1, but 1 is left. What about the 5th one? It becomes a free electron. That's why it becomes conductive. But you need to apply a pressure to it. What is the pressure? What's the pressure? What is the pressure you can add to a piece of material in order to conduct electricity? Pressure is the voltage, right? You add a potential drop, then it's going to drive these electrons to the anode or cathode. Anode, the electron is negative charge, right? So you have a battery, plus minus, to this material. That's a chunk of material here. It's a semiconductor, right? There will be some electrons that's going to flow to the anode. That's why it's called semiconductor. It's not super conductive compared to copper, but has a higher conductivity compared to glass. Why do we have to know this? It's not an analog, but we have to introduce this right now, since you have to understand what's going on for the unwells when you are laying out tomorrow. So that's phosphorus, and it contributes free electrons to the material. So this is called N-type. Just don't get confused, right? It dopes P in there, but it's an N-type. Because the electrons are negatively charged, right? It's a negative, it's N-type. If you dope boron, we don't have boron here, but boron has how many? 5? 3, right? Yeah, boron has 3. So boron, but 5 for the proton, right? It's 2 and 3. So if a silicon wafer is doped by what? Boron, what's going to happen? So these silicon atoms are contributing 1 to the bonds, as usual. What about the boron? Only has 3 electrons. It's going to form a bond here, a bond here, a bond here. What about the other one? It's a very interesting concept, it's in physics. So there's no electron to form the bond, and we call it a hole. Yeah. A potential. So the hole are being treated as a positive charge. And the free electron is a negative charge, and this is a positive charge. And if you apply a voltage to it, it's very interesting. Okay, something I have to ask Dr. Jessing. What's the best way to explain it? But I don't care here. We just care about the circuits. So what's going to happen here is, because electrons are negatively charged, right? If you apply a battery to it, what's going to happen? So electrons is going to be attracted to the anode. That makes sense, right? Why? Because it's a positive charge. It's going to attract electrons. What about this one? The opposite, yeah. So the holes are being attracted to the, the holes? Where? Seriously? It's just a seat. It's empty space. They just think about that in that way. Okay, so the holes are going to be attracted to the cathode. Yeah, that's right. That's how it works. So I think the holes are attracted, so the electrons are moving still that way, right? Does that make sense? Because actually, it's like when you are in physics 1, physics 2, whatever. Okay, so the current flows that way. It doesn't mean that you have positive charge flows that way. It's just like electrons are physically moving, but you consider the current flows the opposite way. Just the definition, but there's no physical thing flowing that way, right? It's just electrons. It's just electrons moving backwards. But we just treat the current, we just define the direction of the current as the opposite way of the electrons movement, right? Same here. Whenever something's flowing in the circuit, it's only electrons, but nothing else. So electrons are being attracted that way. However, it fills the hole and then moves away, just like take a seat and then keep moving. Right, just a dynamically equilibrium. Whenever it reaches the equilibrium, it's filled it up and then goes away. Just dynamically filling it up and then leave the hole. But consider that the hole is moving that way. Okay, there's no difference. Okay, so this type of semiconductor is called p-type. Positive, right? It's not a b-type. I think this is p-type. This is a phosphorus, but it's n-type. Boron is a p-type. But there are other materials can be used as a dopant to form p-type or n-type. These are just two examples. The most popular ones being used as dopants for semiconductor materials, right? Yeah, you will get into the MOSFETs pretty soon. Let's look at it. Very good question, though. You still remember this is logic, right? So you can dope. That's a cross-sectional view. You cut it like a pie. You cut it and look from the side. And this is called a gate, like a device like that, right? It's an n-type MOSFET. We're going to cover that later, but it's called NMOS transistor, and the substrate is a p-type. So they are being used to hold different charges, different voltages. So the p-type substrate, so that's just a silicon wafer itself. So if you got a silicon wafer, it can be n-type substrate, can be a p-type substrate, but the p-type is the most popular one. So we got a p-type substrate, in TSMC or Samsung, right? They have a wafer, and then start doping materials onto it. So first, they got a piece of silicon like a p-type, right? So what's the dopant in the p-type semiconductor? This, right? Okay, and the p substrate, or it's called p sub, is being grounded, and the n plus are the terminals for drain and source. So if you look at the symbol here, it's a drain and source, and here's a gate. If you open it up by using a voltage like 5 volts in a simulation, and they'll give a pressure here, 5 volts as well, and the electron is going to flow into the channel. So the electron is going to flow into the channel. How that works, because if you give a positive voltage to the gate, like 5 volts, what's happening is there's no conductor here, so that's called gate oxide. It's a dielectric material, but however, whenever you apply a positive charge, which is a positive potential, like 5 volts, what are these potentials in the channel? So this is like a channel here, right? If you have a positive charge through a dielectric material like a cap, so that voltage, positive voltage, is going to attract electrons from where? Not yet. So the p-type material, even though the electrons are not it's called majority or minority, right? The p-type has holes as what? Yeah. And electrons are minority in there. So even though electrons are minority, they still have electrons in there. So whenever you apply a positive voltage to the gate, it's going to attract electrons, like all the electrons in here in the substrate, will be attracted, will go up and fill up the channel. Like the electrons are going to fill up the channel. And what's next? If you only turn on the gate, and do not have a voltage here, what's going to happen? Is there going to be a current flowing here? No. Why? Yeah, it's just getting attracted and form a what? It's a layer of electrons, like an electron channel. Just have a cross of electrons over there, staying there, waiting for the command. So what's the command? To drive them in the circuit. Yeah, the drain potential, right? So you add a voltage drop across the channel, right? So it is able to drive them, so they are going to flowing freely in the channel. Why is it? Why we need that? Why is this the foundation of pretty much everything in your phone? CMOS, right? Just CMOS everywhere. Why is that is important? If I have a resistor, you know, I just turn this on or off or give a pulse here. So 5 volts in digital logic, this is high, right? Ground is low. So that's 1, 0, that's digital. If I turn on this, on and off, you turn this on and off, what's going to happen? This is from the circuit because this was 5 volts, right? It's a 5 volts battery. It's grounded as well. So this is a circuit. So current is going to flow in there, right? If I turn this on, what's going to happen? For this node, if this is V out, it's 10K. So for example, this is low here. We're looking at this logic 0 for now. So logic 0 is not going to turn this on because there. Yeah, so here's shut off, right? There's nothing. So what is VO? Why eat up?
Because if the gate isn't open,
what does eat up mean?
Like it's going to be dissipated across the.
Why dissipate?
It goes from 5 volts down to 0 volts.
Why down to 0? There's no 0 volts. It's disconnected. There's no ground. Yeah, so if there's no current, what's going to happen? Wait, this is very fundamental, okay? It's good you guys are here. So if there's no current, according to Ohm's law, I0, so what's the voltage drop? 0. No drop means what's the voltage here? Yeah. Right? So this resistor is considered as a pull-up resistor. Why is a pull-up resistor? Whenever there's no current flowing in here, it pulls it up. Yeah, so now let's look at this. Why do we need a pull-up resistor? If I have 5 volts, I just need this to be 5. Why do I need a resistor there at 10K, not just 1K or just 100? So if when this is 0, there's nothing, right? What's happening? What is VO? Okay, all right. So what if I turn it on? And then what? What is this 5 volts? It's a battery, right? What's happening? Fire. You short the 2 terminals of the battery. Is that good? So what you need? Pull up. Why is it called pull up? Guys, very fundamental. You need to know this. Yeah, no, this is the best example. Whenever you don't have any current flowing into it, it pulls it up to 5, even though there's not that kind of action, pulls it up. It's called pull-up resistor, just remember it. Makes sense? So what if I have let's show an example like that, right? 5 volts, ground, 10K, and here's the out. What is this called? Pull down resistor. Why? It pull it down to 0. You have to have that kind of model in your brain, in your mind. Whenever you see something like that, you feel something is pulling this pin. If you don't have it, you should. As an electrical engineer, you're looking at this, you feel like something is pulling this point down to ground. Whenever you see this, you feel that something's pulling it up. Critical. You will know that if you work with me for another year or 2. There are so many examples or projects you will learn from. Okay, why is this called pull down? Because whenever you disconnect the circuit, it pulls it down to 0. So what if you close the switch? What's the voltage here? Why not 0? Yeah. So it's short circuit, right? It's being shorted to 5. That's why it's 5 volts. It's not 0 volts. Makes sense? Do you have current? If you close the switch, is there any current flowing in the circuit? Yeah, it's a circuit loop. 5 volts is a battery, right? Makes sense? So why we don't do that? If you close the switch, what's going to happen? Fire again. 1 ohm. So now here's another question, another interview question. Another question, okay? I have a circuit network. That's a 2 terminals. I'm going to drive a load. A motor has an internal resistance, usually very low. It's just coils, okay? $50 ohms, for example. And there's another load It's a heater. It's a heating resistor. So a quick question, the heating resistor has low or high resistance? You want to heat it up, so you need what? Yes. Okay, a few questions, right? A heater usually like 70 ohms, for example. And this is 1 mega ohm. Which one is a heavy load? Which one is a light load? Or heavy load or light load? I haven't heard about that. But which one is a heavy load over here? Which ones are, or which one is a heavy load? So we won't pass the interview again. So it's just some really common misunderstanding in circuit 1. So this is a real light load. Why? Because it doesn't require a lot of current. They have 5 volts here. What's the current? 1 microamp. Easy. So you can drive this guy because usual load doesn't only have resistive load, right? It usually has a capacitance in there as well because the capacitance is everywhere, parasitic capacitance. So there are caps all around the cable. The rubber materials and metals are forming all this parasitic capacitance. Make sense? Okay. So you have a resistor like that. Yeah, let's don't talk about the caps for now. It's confusing. This one only requires 1 microamp. However, the heater, if it's only 70 ohms, you get 5 volts here. It requires how much? 5 over 70 ohms, right? Hundreds of milliamps. Okay, what about this motor? The motors are really heavy loads. That's why you need a driver for the motors. Whenever you are working on a little robot car, why not just directly use a battery to drive it up? It doesn't work. You have to use the driver. The driver can rebuffer that circuit because it has all the connections to the 2 rails. So whenever you drive it, use your like digital pin with Arduino. Anyway, so when we are using a digital pin like D0 from the Arduino, are these digital signals powerful or not powerful? Do they have a lot of current in here to drive a heavy load? No, these are just a really light, really not powerful, digital waves. So what you need is you need to connect the driver. Why the driver makes a difference here? Makes a difference. If you drive the driver is going to output the same 1 and zeros, no difference. But why do we need it? No difference. I use the Arduino to toggle it, right, to send that digital signal out. I have to use a driver. There, connect that, the same logic, and output the same logic to drive a motor. Why this makes a difference? I will learn all these things in this class, right? When you are working with inverters, why this makes a difference? The drivers have power supplies, right? And you can connect these ones to high current regulators. No, inverters, different stages of inverters. Transmission gates or inverters, but usually it's just inverters. 2 inverters inverted back and forth. So it's still the same logic. Okay. Why is adding current to it? No, it's not amplifying it. Why is amplifying? It's the same 5 volts logic. It just have, because all these driver devices have connections to the power source and ground. So it has a pathway to source more current from a high current power supply. You know what I mean? Whenever I turn it on the device, it is able to source a lot of current from the high current power supply to fill up the cap. The loads are capacitive, resistive, whatever, right? So something like you have a control, have a valve, and the valve you can use Arduino to control it. But however, the valve connects to a huge pipe, which connects to the ocean, and just want to fill up a little cup. Turn it on, all the water is going to fill it up. You know what I mean? Same concept. When you discharge it, this connects to the sewer ground. So it discharges all the water to there really quickly whenever you turn it off. It's a huge pipe. Charge and discharge. Charge and discharge. Very quickly. That's why you need the drivers. Anyway, but when you're looking at these circuits, keep in mind, it's going to be in the interview question sometimes. 50 ohm is a heavy load. 1 ohm, super heavy load. Have to think about how to design a circuit to drive it. Right? If your power supply or a circuit cannot drive this, which means cannot provide enough voltage or current. Yeah. Then what's going to happen? No. Yes, but anything else? What else? No. Yes, a little bit. Yeah, but what's the most important thing here? What's the most important fact? It's going to lower the voltage. It's going to lower the voltage. Try to provide enough current. You know what I mean? So the power supply is going to lower the voltage. How do I understand that? I got distracted from whatever I should cover anyway. This one. So for example, you have a power supply in the lab on the bench. Okay, you put a 5 volts in there. Put a 5 volts in there, and it's a 1 amp. You set up the power supply to supply as much as 1 amp up to 1 amp current to whatever circuit, whatever load you connect it to. So what's the current in theory? Yeah, it's going to be 5 amp. But can you? No. It's going to happen. When the power supply cannot supply 5 amps, what's this one going to do? It's going to drop the voltage. Why? How can I understand that? Why it's going to drop the voltage? So by learning calculus, and we don't have that kind of class in China. It's just called Advanced Math 1, Math 2. So just 2 math courses in college. And I don't know which calculus class covers that concept. Just think about the infinite way of it. So for example, now it's not 1 amp. It's just as low as 0 amp. It's very close to 0 amp, but it's not 0. Like integral limit or something. I don't know. Like infinite. Right? It's just approach 0, very, very close to 0. What's going to happen? You are shorting 5 volts to 0, so it's going to drop this voltage to 0, right? Whenever the two potentials are super close to each other, 5 volts is not going to 5 volts anymore. It's grounded. It's going to be 0. It's going to lower the voltage. But now it's not a huge difference from the 0 ohms. So that's why it's going to drop it, not directly down to 0, but it's going to drop this voltage a lot. So that's why 1 ohm is a heavy load or light load. Super heavy load. What about 1 mega ohm? Nothing, easy. Very easy to drive. So if you have a 1 mega ohm resistor, and the cap, so that 1 mega ohm resistor is limiting your current. Okay. Do you think when you toggle this source, do you think you can toggle this cap's voltage really easily, like that, sharp edges, or it's going to be like this? Won't be able to charge it up. Which one are most likely to be seen? Hmm? Think about what? The current. So if you have a huge resistor, are you going to have a very small current or a large current? Yeah. If you have small current like droplets to fill up the huge cup or bucket, could you fill it up really efficiently? No, it's gonna like struggling, right?
Yeah.
Okay, which means you don't have enough current. Okay. So tomorrow in the lab, the resistors are called N-well resistors. If this is the top view, you look from the top. That's the layout. And there are two connectors to the two terminals of the N-well. And if you cut it here, right, and look from the side, so it's a cross-sectional view, it's nothing but just a well. And so here's a P-type again, semiconductor silicon, P-type silicon, and this one is called N-well. It's N plus material, but not as heavily doped as N plus materials. They're different. But it's an N-type well being doped into the P-type silicon wafer, and this guy has a certain resistivity, so you can use it as a resistor on the silicon chip. But this is not the only resistor material can be used as a resistor. The polysilicon on the top layer here is the same as a gate, right? So the gates, if you make a super long resistor. But N-well is being used as a resistor as well. And what you need to know is, this is a 3D material, 3D structure. You can imagine, right? It has width, length, and thickness. And if you draw it like that, it's 3D material, and this is the width, and this is the thickness, and this is the length. It's a piece of material in here. Okay, and it has a certain, so the resistance is calculated as rho times L over thickness times width. So the width is here, thickness is here, right? So here's T. So T times W is the area, the cross-sectional area. And times the length is the volume of the material. No, L over it, sorry, L over. So this is A, the area. Remember the resistance of the material? You probably have learned it in physics too, right? It's O equals the length of the material over the cross-sectional area of the material and times the resistivity. Okay? But if you put in here, R also equals rho times L over T, no, actually rho over T times L over W. And this is called the, how many squares? This is something more. I have to take some more time. We'll probably take like 10-15 minutes tomorrow to cover this one. But I think these are also important. Common sense, I need to learn. Really, what you think? I mean, these are very fundamental concepts for you guys to become an engineer, electrical engineer at least.